All right, so this week we're going to continue with the module 13, which is searching and sorting, but we're going to switch gears a little bit, and instead of focusing on the algorithms and efficiency, we're just going to look at it from a practical perspective. How do we do this in practice? In other words, how do we search and sort for things in C without having to write our own functions? And that's what you want to do. In practice, you don't roll your own. And this applies in a lot of different scenarios. For example, in cryptography, this term is actually taken from cryptography, that you never develop your own crypto encryption algorithms. You use what's been vetted and has had a lot of eyes on it and has had a lot of debugging and input on it. Because if you don't, then you're just relying on obscurity. Obscurity is not security. And so we always say, don't roll your own. In other words, you shouldn't have to write your own implementations unless there is a very good reason to do so. And I've never seen a very good reason that couldn't be better handled in a different manner. So, and I'm putting all caps on that one because VGR. Do you have a very good reason? Probably not, right? In practice, you use the built-in searching and sorting algorithms, sorting implementations in the language provided by the language or standard libraries. And this is true of any programming language. Every programming language will have some built-in mechanism or some standard library for you to do searching and basic searching and sorting algorithms. You hardly ever have to develop your own, right? And it has an added benefit. To avoid multiple implementations, you use what's called generic programming. Right? So as we saw last week when we developed our own linear search and binary search, and we talked about selection sort and quicksort, everything that we did only applied to an array of integers. So if you want to have a searching algorithm or a sorting algorithm, an implementation for an array of doubles, or an array of strings, or an array of students, then you need to copy, paste, which is never a good idea. Instead, what you do is you have one algorithm to sort any type of data. And then you still have to plug in a little small piece of it called a comparator function that, given two things, it says they're in order or they're out of order, so they've got to be swapped, or they're equal, so you can leave them alone, right? So they're in order, they're out of order, or they're equal. That sounds really familiar, right? And that's where we bring in generic programming. Most programming languages support it in some way. In object-oriented programming languages, they go full-on polymorphism. Of course, C is not an object-oriented programming language, so we only have a kind of weak generic programming, but it's good enough for everything that we're going to be doing. All right. So to avoid multiple implementations, you use a comparator method function. Right? So what is a comparator function? A comparator function takes two things, right, A and B, and determines their relative ordering. Right? And the way that it tells you their relative ordering is one of three things. It always returns an integer. It returns something, and I'll emphasize that, something negative if A comes before B. It returns 0 if A is equal to B. Right? It returns something positive if A comes after B, right? And if you want to rearrange that, B is less than A. So that's the same exact thing, right? It's just I'm writing it in reverse. So A comes before B, it would return something negative. A comes after B, they're out of order, it'll return something positive, that you do need to swap those because they're not the same thing. Or it returns equal if these two things are the same thing. This sounds really familiar. Where have we seen this pattern before? This is a comparator pattern. strcmp. Given two strings, apple and zebra, it returns something negative. And again, I'm emphasizing there's something. You may or may not necessarily need be able to read anything into the magnitude of that number. It's just going to be something negative, something positive, or zero. And we sometimes slip up and say something zero, but there's only one zero. There is a negative zero, but we won't worry about that. It's still zero. Okay? All right, so why does this work? And to illustrate what we're going to be doing with this eventually, I'm going to just show you a picture from the book. Here we've got this generic sorting algorithm. It could be selection sort, it could be quicksort, it could be whatever. It doesn't know, it doesn't know what these two things are. They could be integers, they could be doubles, they could be strings, they could be students. It doesn't know what they are. So it doesn't know that this one comes before this one, or this one comes before this one, and they're out of order. But it does know how to sort. If it knew that piece of information, it would be able to swap them and put them in the correct order. So as an array, given input to this generic algorithm here, it needs a little bit of help. And that little bit of help is this comparator. Anytime the sorting algorithm says, are these two things in order? I don't know. I'll give it to the comparator instead. I don't know what these things are, but the comparator does. And the comparator knows how to compare them. So I'll go ahead and give it A and B, and it says something negative, 0, or something positive, depending on whether or not they're out of order. In order, out of order, or they're equal. Well, once the sorting algorithm has that information, that generic information that they're out of order, it knows, okay, well, I need to swap those two things. Or if it's quicksort, and you've got a pivot element, and you want to put things that are less over here, and things that are greater over here, well, all it needs to do is ask the comparator. Here's my pivot element. Is this thing less or greater? Was it negative or 0 or positive? Okay, that tells me I need to put it over here, or I need to put it over here, or it doesn't matter which side I put it on because it's equal, right? So you once you've got that missing piece of information here, this comparator, then you only ever have to write one sorting algorithm. And anytime that you want to change what you're sorting, you just need to change your comparator over here, that one little tiny piece. And this sorting algorithm will take care of everything for you. Okay? So how does it work? Let me go ahead and go back over here to the notes. So let's talk about comparators in C. Right? In C, a comparator function, and that is a made-up word. It's not a real word in the dictionary that you can look up. Comparison, compare, a comparator, right, is the nounification. That's not a word either. It's the nounification of the verb compare, right? We usually call those gerunds, right? But that's not the same thing. Running is the gerund of run. Comparing would be the gerund of compare. This is something different, right? It's the nounification. So has the following signature. Right? Again, there are only two things in computer science that are hard. One of them is cache invalidation, and the other one is naming things. So we have to make up a new word every once in a while to get what we're talking about, right? So it has the following signature. Now let me go ahead and go into the next line here. Int cmp const void star a const void star b, right? So let's start taking a look at each one of these things. First of all, what is void star, right? What is that thing, do you think? Well, if I had written instead int star, what would that be? That would be a pointer to an integer. If I had written double star, that would have been a pointer to a double. Void star, it's a pointer to, unfortunately, there's a bit of a misnomer here. It's not a pointer to nothing. In this case, void means anything, right? So we've had void, null, 0, the null terminating character. All right, we've had the concept of nothingness in several different contexts. In this context, we have a word that means nothing, but it's taking on a new meaning. It means anything, right? It's a void star. It is a generic void pointer. Right? It can point to anything, any type of data. It can point to an integer, it can point to a double, it can point to a character, it can point to a structure, it can point to anything. Well, that's the generic in generic programming. In other words, we're not passing in an integer here. We're not even passing in a pointer to an integer. We're not always going to be comparing two integers to say that this one is less than this one. Well, sometimes you're going to be comparing student structures. And so we need to erase that typing and say that this is not necessarily an integer. This is a thing that has a memory location, right? At the end of the day, this is nothing more than a generic memory location, right? So how do we deal with this? It is the comparator's responsibility to recover the type of variable in order to do its comparison, right? And we'll get to that here in a second with an example. And it follows the standard pattern. The return type is an int, right? It's something negative, positive, or 0, depending on the relative ordering of A and B, right? So given these two things, are they in order? A comes before B. Are they out of order? B comes before A. Or are they equal? Because by this comparator's comparison logic, they're for all intents and purposes, they're the same thing, right? That gives you more information than just simply saying that A is equal to B. It gives you the relative information. How do you order these things? Okay. And all right, that's pretty good for now. Let's see. Inside the comparator, you follow a general pattern, right? You typecast the generic pointers into the type of data you intend to compare, right? You then apply the logic to compare them. You then return an integer, right? And it doesn't matter what you return as long as it's negative, positive, or 0, corresponding to the relative ordering of the two elements, right? So for now, let's go ahead and do this for integers. That's pretty easy. Given two integers, we'll go ahead and sort them in ascending order, or we'll order them in ascending order. So let me go ahead and start by making a comparator, right? I'll call it my integer comparator, right? For now, right? Now, should I pass in two integers, int A and int B? Right? Already I violated the whole purpose of doing this exercise. It's no longer generic. Now this only applies to integers. Same problem as we saw last week. If I create a linear search algorithm, linear search implementation, or a binary search implementation, or a selection sort implementation, then it will only ever apply to integers. I want to make sure that I'm applying this to any type. So const int star A, is that right? No, const void star A, and const void star B. By the way, what does the const tell you? That you're not going to be making any changes to whatever these things are, because you're just going to look at them and say, okay, A comes before B, or B comes before A, or they're equal. You're not going to be making any changes to them. And so that's why we label them as const, okay? All right, let's go ahead and apply that first step. You typecast the generic void pointers into the types that you intend to compare. Well, this is a comparator for integers. So what I need is int star. I'll call it x and y instead of a and b because those are already taken. Int x star x is equal to a. Now already it's complaining, but it's a soft complaint because it's a little under squiggly line here, but it's green, so it's only a warning. What is that warning? Initializing int star with the expression type const void star discards qualifiers. In other words, you're trying to force this generic pointer to become an integer pointer. Well, if you're going to force that, then you should force it explicitly. So int star a. Right? And you know what we've done? I've just demonstrated how you can actually violate this promise. Remember I said that const is a promise, it's not a guarantee that you're not going to change anything? Well, if I typecast this pointer into A, well, I'm perfectly able to change it. I'll set it equal to 42. And the compiler will not complain about this. The compiler is complaining down here, but that's for other reasons, because I'm not having a return value here. And if you put one, just a placeholder there, you'll see that the compiler is perfectly okay with this. This is how you can violate that promise. This is how you can break that promise. So what I'm going to do is, okay, fine, I'll keep my promise. I will go ahead and keep it as a const. And now you see that if x is a const, then the compiler does complain about this. You can't change that. You just said that it was a const. I'm going to make sure that you don't change it and give you a compiler error there. Okay, fine, I won't change it, right? But I will need to do the same thing to x and, or to b. I'll call them x and y, okay? Now, this is necessary in a sense. It's not necessary in one sense, in that if I just treat it as an integer pointer and continue along that way, it'll work. But writing this code here expresses my intent, that I'm looking at A and B, and I'm going to assume that you've given me good data. I'm going to assume that you've given me x and y, and they're both integer pointers, so I can treat them as integer pointers on lines 5 and 6. As with anything with C, if you violate my assumptions, then it's on you. It's undefined behavior. Just like if you wanted me to look at an array and you passed me an array and its size, and you lied to me about the size. You gave me an array of size 10, and you told me it was an array of size 20. And then I iterate over that, and I go off of the edge of the array. That's your fault. You lied to me, right? You said it was 20, and I'm going to go ahead and act like it's 20. If you pass me a generic void pointer that I expect it to be an integer, I'm going to assume that you did it correctly and that you passed me something that's an integer. And if you don't, well, then that's undefined behavior, weird results, okay? But now I've got my x and y, right? And they're integer pointers. Now I just need to compare them. If x, can I do this? X is less than y. Well, that means that A comes before B, so they're in order, so I should return what? Something negative. Well, give me something negative. I could go negative 42. Oh, why 42? Weird. Just negative 1, right? Or your favorite constant integer if you want to, whatever. Can I do this? What am I comparing there, really? X is a pointer. Y is a pointer. They are memory addresses. What I'm asking on line 8 is, does X's memory address come before Y's memory address? And is that what I want? No, I want to know, is 5 less than 2, or is 5 less than 10, right? And so what do I need to do to these pointers? Dereference them, right? And if you wanted to up here, you could put in some error checking here. If A is null or B is null, then what do I do? Here it's not really error checking anymore. If you give me something that's null, that's not an integer, and another thing that is an integer, which comes first? Does nothing come before anything else? And so it's kind of like negative infinity, and the null is treated as negative infinity. Then we have all our negative numbers leading up to 0, and then all of our positive numbers going up to the maximum value. I don't know. So I'm not going to worry about that. Again, I'm not going to worry about error handling in this case because I'm just a comparator. I'm going to tell you that it goes like this, this, or this. Whether or not you've got an array full of null values, that's on you, right? If you want to, you can go ahead and create a comparator to handle null values. All nulls should come first. And so that you could say, if A is null but B is not null, well, give it something negative, right? Because this null comes before this thing down here that's not null. Or you want to reverse that, well, then B is null and A is not, or A is null and B is not null or something, right? You can go ahead and implement that logic if you really want to. I'm not going to worry about that at this point, though. Else if, well, if x is greater than y, then they're out of order, and that's the intuition there, that they're out of order. So return what? Return 42, something positive. I'll just 1, right? Keep it simple. Else if x is equal to y, well, now this is they're equal, So return what? 0. All right, because they're equal. Don't worry about that. I don't know why you're still complaining. All right. I know why you're complaining, because you can't figure out that these three things are the only possibility. So should I really even have this check here? It's either this is strictly less than this, or this is strictly less than this, or what's the only other possibility here? That they're equal. So I'll go ahead and return 0. And now it's not complaining anymore. But I did want to go through that to show you that that's the third and an exhaustive case there. Okay. Now you might be tempted to start thinking about little tricks. For example, think about say A is 5 and B is 10. Right? What's one trick that I could do to say take this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but with a few comments there. In fact, I'll add another comment here. They're in order, so return something negative. Right? You might start thinking about tricks. How can I take those 12 lines of code and cut it down to just one thing? And you might figure out a little bit of algebra-wise, well, what if I returned A minus B? Right? Now, this is dereferencing here. Okay, and what are you complaining about now? That should work. Fine. Oh, sorry, yes, X and Y. Thank you. There you go. Now you're happy with that. All right. So here, let me fix that. There we go. So what's this going to result in? If A is 5 and B is 10, 5 minus 10 is negative 5. Hey, that's negative. What if it were reversed? What if it was A is 10 and B is 5? Now 10 minus 5. Hey, that's 5. That's positive. Okay. What if they were both 10? Hey, this works great with my pattern, right? That 10 minus 10, that's equal to 0. I could get away with just this one-liner here, right? You could get away with it 90% of the time until what happens when x is very small, say negative 1 billion, and y is very large, say positive 1 billion. Negative 1, or let's say 2 billion. So negative 2 billion minus positive 2 billion results in negative 4 billion. But is negative 4 billion representable by a simple old int? Nope. What do you have then? You have underflow, and instead of a negative number, now you have a positive number. Right? Don't do tricks like that. Tricks are for kids. Leave them there. Right? Just do if, else statement. That's a perfectly fine pattern here. Right? In fact, that's the preferred pattern. Okay? I don't like that name anymore, my integer comparator. So I'm going to go ahead and call it comp int. Right? CMP comparator or compare int. What would it look like? Now, this is going to order things in ascending order. In other words, 5 comes before 10. Negative 10 comes before negative 5, right? So it's going to order it in non-decreasing order, in increasing order, if you want to look at it that way. What if I wanted to do it in reversed order? Descending order instead. How would my logic look different? That I would need to, in this case, they are, let me go ahead and get rid of my comment here. In this case, I would return positive instead. I would return negative, and I need to reverse 0, but the reverse of 0 is 0. So that'll work. Right? Or I could have changed my if statements here and swapped those around. Or, you know what? Tricks are for kids, but this is not a trick. Code reuse is never a trick. What could I do instead? One-liner. I didn't get rid of my code up there. CMP int on A and B. What could you do to that? Negative 1 times. Flipping things over. Negative 1 times negative 1 becomes positive. So negatives become positive. Positives become negatives. Zeros stay the same. Code golf. Let's get rid of a few characters. What else could I do? Just reverse the arguments, right? And now, that's as good as it's going to get. Code golf is a game where if you write a piece of code that does one thing, And then the next person writes a shorter piece of code that does the exact same thing. And then the next person writes a even shorter piece of code until you get down to the shortest possible piece of code that produces the same output. It's code golf because you're always trying to make it smaller and smaller, just like a golf score, smaller is better, right? Hole in one is better than an eagle. Eagle is better than, what's next? Birdie, then par, then usual par, then bogey, double bogey, and then they stopped naming them after that because stop playing golf if you're that bad. I don't know. All right, so that's as good as it gets, okay? That's all great. Let's go ahead and think about now how to use this. Once you have a comparator, you need to use it. Right? For sorting, C provides the C standard library has a nice generic implementation or sorting algorithm, sorting function, and it's called. I need to find it here. Sorry, find. Got to spell it correctly. Where are you? There we go. I'm going to cut and paste the signature here. Come on. There we go. And here it is. What's its name? What's the name of the function? Quicksort. What do you think it is? What does Q stand for? What did we look at on last Wednesday? Quicksort, right? Now, it's only called Quicksort because the original implementation, maybe it was Kernighan and Ritchie, I'm not sure. I'm not sure who to blame for this. They should have just called it sort. But when they implemented it, the first iteration that they implemented a version of Quicksort. Now, it doesn't necessarily have to be Quicksort. In fact, on my BSD distribution here on this Mac, I believe that it's a version of merge sort. You can go ahead and you can implement, and some versions use heap sort or tim sort, or there are dozens of other fast sorting algorithms. It doesn't necessarily have to be Quicksort, but because it was named Quicksort 40, 40 years ago, it still needs to be named Quicksort, otherwise that would break code. All right? So first of all, the return type is void. It's not going to return anything, right? And it takes 4 arguments. Well, void star base is the array you want to sort. Well, what can you tell? What kind of things are stored in that array? Are integers stored in that array? Are doubles stored in that array? Are strings stored in that array? The answer to all of those is yes. Why? Because it's a void pointer. It can take any type of array that you give it. All you need to do is make sure that if you give it an integer array, you also give it a comparator for integers. If you give it a string array, you need to give it a comparator for strings. If you give it an integer array and then give it a comparator for doubles, you're going to have a bad time on that because it's going to treat everything as doubles, and they're not doubles. Right? So you're going to have undefined behavior. The second one is nel, right, is the number of elements. That is the size of the array. Right. And then the size, unfortunately, it's unfortunately named here, but it's a different size. Size is the number of bytes each element takes. Right? Now, why would it need to know this? It needs to know this for the same reason that malloc needs to know how many bytes you want. Because if you create an array of 50, or let's say 100 integers, well, that's 4 bytes each, so that's 400 bytes. But if you want an array of 100 doubles, that's 8 bytes each, so that's 800 bytes. Similarly, when Quicksort is going to be changing stuff around, it takes this integer and this integer. Oh, they're out of order according to your comparator, so I need to swap them. How is it going to swap? It needs to know how many bytes actually need to be swapped. If it's an integer, it says, oh, these 4 bytes and these 4 bytes, I need to swap those 4 bytes. Or double, 8 bytes over here, 8 bytes over here, I will swap those 8 bytes instead. And so Quicksort needs to be told how big each one of those things is, because if you're going to be sorting anything, then you need to give it sufficient information on how to swap those things around. Finally, the last thing, compare is a function pointer to the comparator you want to use to order elements. We'll talk about function pointers here in a moment, but it's more important to learn how to use these things before we learn how they work under the hood. So let's go ahead and come back over here to our example. I've got the same array that we were using before, and instead of calling my implementation of selection sort, or maybe somebody's some random internet website's implementation of Quicksort for integers, I'm going to go ahead and call Quicksort that's built into the standard library here, Quicksort. All right? Now, Quicksort needs to know, I'm going to sort this array here, which is 9 elements. So we need to to give it the correct things here. So the first argument is the thing that you want to sort, ARR. Now, this has a generic void pointer, but this is technically an integer pointer. It's just a little bit different syntax, right? Because we're doing a static, an initialization along with the declaration. That's the same thing. We don't need to reference or dereference. We don't need to do those things because it's already a reference. An array is already a memory address. It's a memory address that points to the first element in the array. Then each index is an offset, a memory offset to the next element. Then I need to pass in nel, number of elements. And in this case, that's simply n because I stored it in another variable. I need to pass in how many bytes each thing that I'm sorting takes. Well, I'm sorting integers, so how do I know how many bytes an integer takes? I could put 4, but better to use, as you said, size of int. That will always work. And finally, I need to pass in the comparator that I want to use. Let's go ahead and use this comparator right here. Now, is this correct? Well, first of all, if you have a function and you put parentheses after it, you're invoking that function. In other words, you're telling C, go ahead and start executing this function. That's not what we want to do. We want to take a function and give it to another function to tell that function, use that function over there, or use that function over there, or use that function over there. So you do not call the function. In fact, it's giving me a compiler error when I try to do this. Instead, I need to pass in, basically, I need to pass in the memory address where the code can be found that holds a function that I want you to use. Right? And the way that I do that is, just like arrays, the name of the function is its memory address. So, oops, there we go. I didn't want all of them deleted there. I'm simply passing in the name of the function. Right? No parentheses, just the name itself. Right? And what are you complaining about? You're probably complaining about this. Where is it located? In the standard library. Right? And now you're not complaining. Right? Let's go ahead and execute this and clear this out here. So if this executes correctly, we should get this thing in sorted order here, in ascending order. 0, 1, 2, 3, 4, 4, 5, 5, 9. We didn't lose a single one. Awesome. Right? What if I wanted to sort this differently? What if I wanted to sort this in descending order instead? How would it look differently? I still pass in the same array. The size of the array hasn't changed. The number of bytes an integer takes hasn't changed. The only thing that you do differently if you want a different order is the comparator. And when you do this, now it's in reversed order instead. Right? So you don't have to reinvent the wheel. You don't have to re-implement it every single time. All you need to do is implement this one little piece. One little piece of the puzzle that you have to take care of is the comparator down here. You plug it into the sorting algorithm. You make sure that all your inputs are correct, and it'll take care of it for you. Generic programming. Write one function to rule them all and have that sorted out for all of eternity, right? You don't have to write your own sorting algorithms. All you have to do is write your own comparators, okay? Let's get a little bit more practice here before we move on to the under-the-hood details here. And to do that, I want to look at, let's say, student. There we go. here is a structure. How might we do this with structures? Of course, you can go ahead and do this with doubles. That's pretty straightforward. In fact, let's do that first. How would this look if you wanted to do doubles instead? What would be different? Well, first of all, can you use CMP int? Not twice. So CMP double or double, right? And you don't cast them as integers anymore. You cast them as a double, 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 double. There. I don't know why you want me to do that, but whatever. All right. Any difference? Nope. Same logic, right? Now here, if you tried to do that trick where, if you tried to do that trick of return the difference, now you're even in bigger trouble because what's the return type up here? An integer. So if you go, I don't know, 0.75 minus 5, what's that going to, what is that? It's 0.75 minus let me write it out. 0.075 minus 0.5. Well, what's the result there? That's going to be 0.25. But since you have to return an integer, what is 0.25 when you truncate it as an integer? 0. Is 0.75 and 0.5 the same number? No. Again, tricks are for kids. Don't do them. Right? So don't do the difference trick. Overflow, you risk it. With doubles, it's actually completely incorrect. Okay? All right. So now let's look at it with another example here. Say a student object. A student has an NUID, a first name and a last name and a GPA. I did this just for a variety, to get a variety of data types here. Now let's go ahead and make a comparator, and let's document it. This comparator takes two student instances and orders them by last name, comma, first name. In other words, Smith, Jane, and Smith, Allen, right? Allen should come before Jane because they have the same last name, so all the Smiths are going to be together over here. And then if you have the same last name, we need a way to break the tie, and so we go to the first name so that you can list all last names first and then all first names, and within that group of last names, you order them by first name, right? So let me go ahead and start implementing this function. Int compare student by name, right? Is it going to be student star A, student star B? Yeah, is that a comparator? That's not a comparator. Right? Remember that over here, what does it require? It requires a comparator, which passes in a const void star. All right? This is not a comparator. The only thing that is technically a comparator in C is something with this signature. It returns an integer and takes two const void pointers. Okay? Follow the same pattern. Well, A is not a student, so we can't do anything with it, like say A last name and then compare it with B's last name, right? We can't do something like this and call string compare, strcmp on this, because those are not students. A and B are not students. A and B are just generic pointers. They point to a memory location. If you want to treat them as students, you need to do so. You need to create new variables here. Const student star x is equal to const student star, an explicit typecast on A, and an explicit typecast on B for Y. Right? And now you can treat them as students. Right? What I'm going to do is, well, let's look at their last name. And I'm going to capture that value into a result, into an integer. Not A's last name, but X's last name, and Y's last name. And of course, now that I'm using strings, I need to bring in the string library. Right? I don't want to compare this. strcmp is technically not a comparator because it explicitly takes two const char stars. So we can't use it directly as a comparator. You have to do a little trick with it, and if you want to, you can check out the book, what the trick is, because you'd actually be sorting an array of strings, which is different than an array of characters. If you wanted to sort an array of characters, then you've got a char star, and that'll just take Smith and then put, let's see, I at the beginning, then M, T, H, S, right? It'll sort the actual string and screw it up. That's not what you want. You want to compare an entire array to another entire array. You want to compare a string to a string, apples to apples and oranges to oranges. So I need to force them to become a student, then look at their last name directly, and then I can use strcmp here. Now, what if the result is 0? If the result is 0, then what does that mean? I've got Smith and Smith. They have the same last name. So if they have the same last name, let me increase the size here just a little bit and go down. That's too much. There we go. Same last name, break ties using the first name. Okay. Well, that's pretty easy. I'll just use string comparator again, but not on last name. I'll have their first name, first name, and first name, and you need to stop auto-correcting whatever you're doing there, right? Return that value, okay? Now what if we have Jane Smith and Jane Smith? You can go one level deeper if you really want to and look at something that can break ties, like their NUIDs are unique. But if your sorting algorithm doesn't really care about it, Jane Smith, well, if it's like this or like this, it doesn't really matter, then you can just leave it like it is, right? Otherwise, if comparing their last name gives you a non-zero value, say Anderson and Smith, right? Then you need to put Anderson first and Smith down here. So you can simply return that value, return result. Right? If it's, I don't know, Smith and Zorinsky, right? Then, or Zorinsky and then Smith, it'll return something negative so that the sorting algorithm will put them back into order. Right? And I don't have an example here, but that's essentially what you would do here. Okay? Because I guess we could do it really quickly. No, I'd need at least 2 or 3. I'd need at least 3 student instances in order for this to actually make sense. But you'd follow the same pattern over here. Instead of ARR, it would be some array of students. The number of students in your array, size of, not integers anymore, but student, right? And you would pass in a different comparator. You'd pass in the comparator for students by name. Right? What if you wanted a comparator for students by GPA? This is comparator. Orders. Note here that I'm saying orders. It doesn't sort anything. Q-sort is what sorts. This only orders them, that it goes like this, or they're equal, right? This comparator orders 2 student instances by GPA. Oh, GPA, ascending or descending? Do we want the 4 O's up here, or do we want the 1 O is up there? Does it go down? Yeah, 0 is up here. Right? Blutarsky, right? Blutarsky is up here. All right, if you don't know who Blutarsky is, then y'all need to watch Animal House. I'm saying that's his name, right? Blutarsky. No, nobody knows. All right, Animal House, Blutarsky. Yep, that's his name. Animal House Blutarsky. He had a perfect 0.0 average, right? Because he never did anything. All right, so we've got GPAs, 4 O's. We'll go ahead and put those first at the top for honor roll stuff or something. In descending order, right? So same thing here, comparator, but not by name, but by GPA. Right? And I will follow the same pattern of casting them as students. Right? Now I could write out, in fact I could copy pasta here. I could copy pasta this stuff up here, except wait a second, you're copy pasting stuff for comparing 2 doubles with each other. Well, maybe you could go ahead and reuse that instead. Compare a double. X's, in fact, I want let's see, Y's GPA first, then X's GPA second. And the reason that I want that is because I want it in descending order. If I wanted it in ascending order, then I'd go X then Y. But I want it in descending order, so I just switch them around. And then I'll return this. And it's complaining for a reason. What can anybody suss out that reason really quickly there? Well, go ahead. Anybody got an idea? What is this thing right here? Well, Y is a student star, so it's been dereferenced using the arrow operator here. So all we're doing is this GPA up here. It's a plain old, regular old variable, GPA. What does compare double require? A pointer. So how do we take this plain old regular variable and change it into a pointer? Do you remember? Ampersand and ampersand. Right? And now, unfortunately, here at this point, I don't remember the order of operations of any of this stuff. So I'm going to have to be explicit about it. In fact, I think that was the warning there. I'm going to go ahead and, oops, there we go, and put in those parentheses there because I forget I forget what the order of operations there is. And why are you complaining still? Oh, because it's down there. Fine, I'll move you up. Order matters unless you use prototypes properly. I'm not using prototypes properly here. But now you should not complain anymore. There we go. Right. And again, I'm not going to be able to demonstrate this because I didn't set up any examples prior to this. But there are plenty of examples in the book. Okay? Okay. Let's see. Where is it? There we go. So how does all this work under the hood? Question? No? Okay. All right. Just tired. All right. Gotcha. Don't worry. Function pointers. So I mentioned that this thing up here is a function pointer. Look at that syntax. Right? Let me go ahead and expand this out so that we can see it a little bit better. This is brand new. Oh, this seems like brand new syntax right here. What is this thing? This thing is not a regular old variable like int x. It's not. It's more like a pointer variable because it's got this star over here. This thing is actually a combination of two things. It's a pointer, so it's a memory address, but it's a pointer not to an integer, not to a regular old variable. It's a pointer to a function. Okay, and that's what we're going to look at with the remainder of our time here. How do function pointers actually work? Right? So the question, the whole motivation for doing this is how can we pass a function to another function as a parameter? Right? And I'll make sure that, let me go ahead and grab this before it refreshes. When I close my computer, it refreshes, so I don't always get the code. I'll put all the code at the end here so that you have it in the notes when I check it in. So how do we pass a function to another function as a parameter? And in fact, why would we want to? All right? These doing so are generally referred to as callbacks. All right? That is, functions passed to other functions so that those functions can call the functions. Right? The function that you're giving it is calling it back. So I've got a function A, and I want to give it to function B so that B can call A. And I'm not calling A directly because that doesn't do anything. Quicksort is what needs to call this comparator over here. I don't call the comparator. Quicksort does. But Quicksort needs to know which function do I call. Do I call CMP int, or do I call CMP int descending, or do I call something else because you're doing doubles instead? I need a way of giving this function to that function so it can call it back, right? And that's why we call them callbacks, right? You're referring back to that function over there. It's a callback to that function. Another example, right? And this is something we're going to be doing after the break, graphical user interfaces, right? You can define a button that, when clicked, performs some action, right? You know, you can create a button, a save button. And when you click that button, it goes and it takes the word processor file that you're doing right now, and it takes it and writes it out to disk. It calls fopen, and then it writes each one of those lines to the output, and then it calls close, and that's how it saves the file, right? Well, you need a way to register. To do this, you need a way to register the function that should be called when someone clicks the button, right? And this is called registering a callback, right? And the way that you do that in C is through function pointers. Call that function over there, the one that I am pointing to, right? And the way that you do that is through function pointers, right? And the other example of immediate concern here is that Quicksort needs a way to order elements. You pass in a comparator function using a pointer to it. Right? Point to that function over there. That's the function that you want to use, right? But a function is code stored in memory. Right? Thus, it has a memory address. Everything in a computer is a 0 or 1. Every single 0 and 1 is stored at some location in memory. Therefore, everything in a computer has some memory address that you can potentially use. Right? It makes sense that you can create a pointer that points to a function, just like you can create a pointer that points to an integer. Right? Because where is an integer stored? It's stored in memory. Where is a function stored? It's also stored in memory. So if you can create a pointer to point to one of them, you certainly can create a pointer to point to something else. You can also create a pointer that points to your own code. Well, a comparator is your own code. And when you do that, you can start manipulating your own program. You can write programs that modify themselves because they can refer to their own memory locations, right? It's very useful sometimes to be able to do that. You can also be nefarious about it, right? If you, for example, you can trigger a buffer overflow, and the return address, when say that you've got the call stack here, and what you can do is if you can manipulate your own memory, you can manipulate, or somebody else's memory, you can manipulate the call stack so that when this gets popped off, you don't return back to this stack frame. You go over to this function over here that has my malicious code in it and start running that code over there instead. Right? If you can do things like that, then you can start making programs do things that you want that they were never intended to do. Right? So, with great power comes great responsibility, like Uncle Ben said. So make sure that you are that you're using this power wisely. All right? I'm just going to show you the basic syntax. So let's create a pointer called ptr2func function that can point to any function that returns an integer and takes 3 arguments: an integer, a double, and a char. So to do that, all you need to do is use the following syntax. You specify the return type. Then in parentheses here, because of order of operations, I will put a star because you have to indicate that it's a pointer. ptr2func, because that's what I wanted to name it up here. And then following that, the argument list, double and char. Now, my pointer is called ptr2func. If I want to make that point to something, I can. But if I don't, I don't have any functions readily available that return an integer and take 3 values: an integer, a double, and a char. So let's think about another function here that we do know what the return types are and what the parameter types are. So let's go ahead and declare a pointer that can point to maths sqrt function. Well, maths sqrt function, it takes how many parameters does it take? The input parameters. You want the square root of 4, so it only takes 1 parameter. All right, and I'll go ahead and call it ptr2 sqrt. Right? And what's its return type, though? Square root of 2 is going to be 1.41, blah, 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 blah. So its return type is a double. Right? And I make sure to put the parentheses there with a star and then the name of my pointer. Okay? And its parameter is only one thing. It returns a double. Right? Now, at this point, what does PTR to SQRT point to? At this point in the program. In fact, let me go ahead and cut and paste this. And I've already taken care of this, so let's go ahead and get rid of all this stuff. And let's actually do some live coding with this stuff. Right? So declare a pointer that can point to mask SQRT function. Great. What does it point to? Nothing. Or uninitialized. It could point to a memory location that doesn't even contain my code. And this is how you can start to manipulate programs and get them to do things that they were not intended to do maliciously. Right? Don't point to your code anymore. Point to my code and start doing something else, sending me your passwords instead, right? Or your SSL keys or whatever. So nothing or uninitialized. So let's make it point to SQRT. Now, how do I do that? PTR to SQRT. Now, if this were just an int star x, you could say that x is equal to, in fact, let's do the review here. If I've got int x is equal to 42, int star PTR to x, how do I make it point to x? Is it like that? It's giving me a clear warning here. The thing on the left-hand side is a pointer. The thing on the right-hand side is a regular old variable. So how do I take this regular old variable and change it into a pointer? Ampersand. Same idea down here. How do I take SQRT, which is a regular old function, and change it into a pointer? You can do this. Except for, just like arrays, square root is already a pointer. So, or simply PTR to SQRT is equal to square root. Right? And now it's pointing to that thing. It's complaining here. Why? It doesn't know what math is. Now, it knows what math is. And I can point to square root. Right? Okay, I've got square root, and I've got a pointer to square root. Just like up here, I've got x, a regular old variable, and a pointer to the regular old variable. If I wanted to manipulate the contents of that regular old variable through its pointer, I would need to do something like this. PTR to x is equal to 101 now. Right? I dereference it, and then I can I dereference this pointer variable and make it into a regular old variable so I can assign a value to it. What do I do down here with this pointer now? PTR to a square root. I can go ahead and call it just like a regular old function, 2.0. Double y is equal to this thing. Right? And let's print that out. Print f, percent f, or square root of 2 is percent f and the line and y. Right? There we go. Let's run it. 1.41 blah, 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 blah. Right? I think I misspoke earlier. The square root of 2 is 1.41, something, something, something. Right? Now, why would you ever want to do this? Why not just call square root directly? Right? Well, it's because you can, you wouldn't do this, right? If you just have the function, just call the function. Don't make a pointer to call the function. But what if you wanted to pass that function to another function? Right? So void run math. Right? And what we can do here is we can pass in a value, x, and we can pass in a pointer to that, so to a function that takes a double and returns a double. So let me go ahead and change this to double. Right? I'm just making this up as I go. Let's make sure. So double star PTR to func, right? And it takes double. There. Now, what function is this? It's just a pointer. So I could say return PTR to func of x. Right? One run, that could be sine. One run, that could be square root. Another run, it could be anything. Right? And I'll show you. PTR to, let me go ahead and say run math instead here. What was it? Run math? yeah, there we go. Run math on, let me go ahead and create int, or double, x is equal to 2.0. Run math on y is equal to run math on x and sine. Right? And then we'll print it out. Printf y is equal to %f and the line y, oops, comma. And what's sine of 2? Remember, it's radians, so I don't know. Oops. I already declared x up here. Let me get rid of this stuff. There we go. Run that again. That looks about right. I'm not sure what it is. But I could go ahead and try to make it equal to pi 3 point, well, here, m sub pi. What's the sine of pi? 0, right? All right, let's run the same thing, but for cosine instead. Right? Cosine of pi is 1. Great. In this case, -1. Right? I could run it on square root instead and get the same answer. Oh, not the same answer, but the square root of 2, or what is it? The square root of pi is 1.77, right? This enables you to pass a function, a generic function, into another function. As long as all of these collection of functions have the same signature, in other words, they return the same value, same type, and they take the same number of and types of parameters, you can go ahead and make all of your make your math make running math generic, completely generic. Okay. Now, this is a toy example, right? Toy examples aren't very motivating. Again, I still don't see the point to this. Why don't you just call sine? Why don't you just call cosine? Why don't you just call whatever, right? Let's write a generic linear search method now, all right? Int linear search, right? And what I'm going to do is I'm going to kind of copy what we have over here with Quicksort. Right? There we go. We've got an array of things, the number of elements in that array, and the number of bytes in the array. Oh, actually, we don't need that, so I'm going to go ahead and get rid of it, just to simplify. All right. Now, how can we implement this one linear search algorithm and never have to worry about this problem again? This is a linear search algorithm that will operate on integers, or doubles, or strings, or students. Right? How can we do this? Actually, I will need the size, sorry. There we go, now that I think about it. Okay. So let's repeat, and this is just off the top of my head, so we might screw this up and we might have to come back on Wednesday and fix it. But let's go ahead and repeat what we did with linear search, but for integers. For int I equals 0, I is less than null, in this case, number of elements, I++, right? Oh, one thing that I forgot to do here is we have to be searching for a needle in a haystack. We've got our haystack here. Let me go ahead and add our needle, void star key. Right? And we're not going to be making changes to it, so we can actually make this const. We're not going to be making changes to this, but those are just cosmetic changes there, okay? Don't worry about that. I can change this to an integer if you really want to, and then you'll stop complaining. Int null. All right, now what are you complaining about? Oh, n and n. Oh, okay. Let me give myself some more room. There we go. There we go. Right, maybe it wasn't complaining earlier about the size, but I'll go ahead and make it into an integer here. All right. Now, before, when this was integers, I would do something like this. If base sub I is equal to the key, then I will return I, the index at which I found it. Otherwise, if we get through the entire thing and we don't find what we're looking for, then I'll go ahead and return -1. There we go. Okay? Now, that's not going to work here because this is not an array of integers, and this is not an integer. Right? We don't want to take the same route as the comparator and force them to become an integer just so that we can use equals equals. We're going to take that and we're going to offload that question to the comparator itself. Right? So I'm going to pass in compare. I'm going to pass in the thing that I want to compare. is the ith element the thing that I am looking for, right? So something like base of I and key, right? I'm going to pass those through the comparator, and if the comparator returns 0, then that means they are equal, and that's the thing that I'm looking for, right? Now, we're still not there yet because base is not a... what does this comparator take? It takes a const void star and a const void star. Well, key is perfectly fine because that's already a const void star. But how do we make this thing into, which is a regular old variable, the ith value there, how do we make it into a pointer? Ampersand. This still is not there yet, right? If we run this, then we'll get kind of weird results. And we're going to get weird results because we're kind of ignoring the size, all right? I is an offset. If this were an array of integers, then I would have a memory address pointing to the beginning. The next one would be 4 bytes over. The next integer would be 4 bytes over. And the compiler would take care of that for me because the compiler knows this is an array of integers. So 4 bytes, 4 bytes, 4 bytes, 4 bytes, 4 bytes. I know where everything is. You want the ith element? I times your 4 plus your memory address, that's how many bytes I need to go over, right? In other words, the compiler knows that you just need, if you want the ith element, come on, I don't know why it keeps doing that, but you want the ith element, right? So base of I. To do that, the compiler would say, okay, base, that's a memory address. Now go over I times the number of bytes each element takes, and that's where you should look for it. Right? If it were 4, then it'd be 4 times I. If we start at, this is why we start at 0, because 0 times 4 bytes, well, that's 0, you start at the beginning. Now 1, the next element, the second element, that's 1 times 4 bytes over. 2, that's 2 times 4 bytes, that's 8 bytes over, dot, dot, dot. Right? The compiler doesn't know that these are integers, and so we have to do that math for ourselves. Right? How many bytes does each one of these things take? Base of I is at memory location. What? Base plus I times. That's why we pass this in. We need to tell it how many bytes there are, size. Right? So we can't use something like this. We need to do our own pointer arithmetic. Base plus I times size. And that's when we use the square brackets in C, that's just us relying on syntactic sugar and the compiler to do our math for us, right? And that's why we start out at 0, because the math is easier that way. And that's how pointers actually work. That's how arrays actually work, 0 indexing. It's an offset from the beginning. How many bytes do you go over? Well, if it's an array of integers, it does the math for you. 4 bytes over, 4 bytes over, 4 bytes over. If it's an array of doubles, again, it does the math for you. 8 bytes over, 8 bytes over, 8 bytes over. But if you make it generic and it's void, it doesn't know how many. Is it 1 byte over? Is it 2 bytes over? Is it 100 bytes over? 40 bytes over because you've got a student? You need to be able to tell it that. And if you tell it that, you need to be able to do your own arithmetic. Right? Base, the beginning memory address, I times as many bytes as it takes over, and that's the thing that you're searching for. Right? So now that I've got this, let's actually use it. I'm going to have to restore some of the stuff we did over here. I want to restore my main. Here we go. I won't Q-sort it anymore. Instead, I will just call my linear search on the unsorted one. So array, and the key that I need to search for is, I'll pass in the key here, right? And I'll create an int key. I want to search for, say, 9. 9 is at index 1. And get rid of this. Array, there are n elements in there, size of integer, and, okay, now I have to restore that. Where is it? There we go. I'll bring this back over here and bring it over there. There we go. And now it's happy about that. except it's not descending. There we go, int. And then let's print it out, printf found key at index, whatever, and the line, the key, and I need to capture that, I guess, int index is equal to, and index. There we go. Let's see if it works. Hey, it found it at index 1. Right? What if this were now an array of doubles instead with a different size? Let me go ahead and go down here and do that. In double array, or array, 3.14, 5.2, 3.1, 3.4, 33.4, and 10.5, right? And we'll do it like that. I don't want a big array. Int or n is equal to 4 now. There are only 4 things in there. And let's go ahead and create the key. I'll be searching for, say, 5.2, right? And index is equal to a linear search. Oh, say what? Okay, double. K, there we go. And I'll have to change that to K. And instead of array, I'll put in br. N is for a size of, it's no longer 4 bytes, now it's 8 bytes. And I can't pass in a comparator for an integer anymore. I have to pass in a comparator for doubles, which is, I had it, where? There we go. There we go. Bring that in. There we go. And double. And then let's print that out again, except that it's going to be K instead of key, right? Okay. And is that good? Say what? Oh, yes, thank you. %f, there we go. So it should find 5.2 also at index 1. There we go, yay. Or 10.5, that should be found at index 3, right? So the whole point of generic programming is so that you only have to write one solution and you're done with that solution for the rest of your life. You have one implementation of one algorithm, and if you make it generic, then you can pass in a new comparator, you can pass in a new, just the thing that's necessary to make it generic, right? And that way you don't need your own sorting function. You don't need your own linear search function. Now, I haven't talked about the searching in the standard library, but I will do that on Wednesday, sorry. There is a B search algorithm. What do you think? Oh, a binary search algorithm. I gave it away. It's called B search, and it's in the search.h library. There's also 2 implementations of a linear search algorithm. It's called lfind and lsearch, right? And they have slightly different behavior. One of them inserts an element if it doesn't already exist. So, and the other one just searches for it. And they all return pointers instead of indices. So you'll get more experience with that in lab tomorrow.